we've gotten to the point where I hope you see what morphing would look like in principle, moving along the manifold. And I don't know how to use a clicker. So just so you walk through, here's exactly what morphing will look like. We'll take the latent model, so we'll generate something in the latent space. We'll morph using the supervised model so that the predicted odds of release go up. We'll show these side by side to subjects and ask, what do you think the algorithm is seeing here? That's the essence of it. So it'll go back to algorithmic prediction, human recognition. Okay? So the benefit of this technique, just so you get a sense of it, is that this kind of pairwise comparison isolates differences. For example, if we just showed pairs of actual mugshots to people and said one was released, one was not, there's an interesting curse of dimensionality here, because there's so many things that differ between a pair of random people. You have hundreds of thousands of things that you can name. So there are many other irrelevant differences that get in the way of interpretation, but by morphing, we're holding as much of the other stuff constant as possible. That's the goal, that's the hope. That's in principle why this improves on things. So there's a curse of dimensionality in interpretation, which as humans can make it hard for us without techniques like this. So just so you get a sense of how it works, instead of showing you what morphing does to the unknown predictor of the judge, let me show you what morphing does to another predictor I made up, one that's all very familiar to you. So I build it, I predict it, and then I do morphing. So this is what it does, and you can see what the predictor I made up was. If you didn't know it, you'd say, oh, that looks like age, and that is indeed the predictor I built up. So we do some tests with known predictors, and they work pretty well. So now let's move to the unknown detention predictor and have people look at the morphs. So this is the pipeline, and this is an example of a morph that we produce moving from left to right. This is high predicted detention probability. This is very low predicted detention probability. On this screen, it's kind of hard, maybe hard for you to tell. We'll get to what it is. We'll show people these image pairs. Subjects inspect it. Here's what the task exactly looks like. They're asked first to guess which of these pairs do you think has higher predicted release. They're given feedback. They're given a chance to learn. They're given incentives to get it right. At the end, they're asked, what features do you think is at role here? And what you tend to, so these allow people not just to do stuff off the bat, but to learn something and see what's happening. You can also subset to the subjects who really got it right all the time and do that type of analysis. But this gives you a structure to play with it a little bit. So let's see what they find. So I'm going to show you the word cloud of what subjects say after seeing these morphs. This is kind of the word cloud. I don't know if something jumps out at you all here, but if you tokenize and put all this together, what you start to see is that about 40% of the subjects all say, what I see is well-groomed. And in fact, that's just what you find. You find that well-groomed defendants, if you have an independent set of subjects, just look at images and rate them as well-groomed or not, that's very predictive of what the algorithm will predict. But of course, that only explains about 2 to 3% of the algorithm's prediction, which if you're keeping score, is bigger than race, age, skin color, all psychological features put together. But let's keep going, because now that we've morphed in one gradient, we still have a lot left. So we can now iterate. So what can we do? How do we find the rest? There's kind of a technical challenge now. Here's what I'd like to do. In face space, I'd like to follow the gradient after orthogonalizing against well-groomed, so I'm now moving orthogonal to that space. Does that make sense to everybody? That's what I'd like to do now. Go ahead, yeah.
Just to clarify, doesn't something like well-groomed have a lot of correlation with factors like race and age? Because those biases seem to be subsumed within well-groomed. Well-groomed is interpreted differently depending on your race, your age, and so on.
Oh, yeah. What this tells you is that's not the case in the sense that well-groomed is far more predictive than race age. In other words, you might think well-groomed is highly correlated with race and age, and in fact, it's not. There's just a lot of independent signal, and that's what's doing all the work.
What is well-groomed?
whether you have a tidy beard, whether you have, if I took my face off, I could give you an example of a perfectly well-groomed person. No. I could point out people in the audience if you'd like. Let's do that. This might actually turn into a fun talk finally. Yeah, if you know what I mean. It's like stubble, hair everywhere. Some people are starting to squirm a little bit. But that's what well-groomed is. It's tidiness of hair, tidiness of facial features, a general sense of like unkemptness in the face. So,
what does tidy hair mean?
Well, no, but that's the interesting thing. These are not objective notions of tidy hair. These are subjective notions of tidy hair. And so it's not a bad question to think they're highly correlated with race. What this is telling you is maybe there is maybe a little correlation, but that's not what's doing the work. Because this is all conditional on all of the other variables. Yeah?
So I was just wondering, like, where does the well-groomed come in the model? Like, how do you use that to predict?
Oh, sorry, no. I didn't design well-groomed. I just have a black box model with pixels. This morphing exercise is telling me that humans guess that the algorithm is looking at well-groomed. And then what I do is I take another set of images. I have raters rate the mugshots on well-groomed. And then I say, does that well-groomed rating predict the algorithm's prediction?
So you're seeing one of the subsequent experiment that.
Yeah, does that make sense? Okay. Yeah. I certainly had no view that it would be well-groomed. So how do we find the rest? We want to do this orthogonalized morphing. There's actually a really interesting technical challenge here that I just want to lay out for all of you. We spent about 5 months on this, so it's fair to say. Let me walk out what it is. Orthogonalizing in GAN space seems really straightforward, but it's not, for one very simple reason. I do not have well-groomed represented in GAN space. I just have latent vectors. Then you say, what's the big deal? Why don't you get a predictor of well-groomed? Well, let's say I had a predictor. That's what we did. So you get a predictor of well-groomed. You can orthogonalize against predicted well-groomed. But remember, the predicted well-groomed has error. As I move, I'm accumulating error. Now you might say, whatever, that's just noise. It's not. It is bias. It'll accumulate in a particular direction, the direction that's correlated with the omitted part of well-groomed that I mismeasured that is still well-groomed. So if you try and do that type of orthogonalized mapping, you actually end up moving along the well-groomed gradient all over again. You're like, what did I do wrong? So there's a lot of subtlety here. Yeah?
But can you not do this thing where you take the kind of Laplacian on this GAN and then look at the eigenfunctions and then decompose your well-groomed direction into...
But again, you don't have well-groomed. That's the thing.
No, but I mean, you could write it as in the basis of eigenfunctions with Laplacian.
Oh, I could if I had well-groomed. I don't have well-groomed in GAN space.
No, but I mean, you have that as a function of the GAN space.
No, I have predicted well-groomed as a function.
Okay. Yeah. Still, the predictor you could write as well.
Oh, you can, but then you have the same problem here again, because the error in the predictor accumulates as you move. Because the error...
I wouldn't be moving anymore, just decompose in my space of Laplace eigenfunctions. So there's no motion really, it's just now a Hilbert space in which I'm just decomposing.
Say you've decomposed, now I've got an image and I want to morph. What would I do?
Well, I mean, I have the, I know that the function which is well-groomed is 10% of this eigenfunction plus 5% of that function minus 3% of that eigenfunction. I keep that linear combination constant.
That's right. So you are morphing holding constant predicted well-groomed. So you're not holding constant actual well-groomed. So if predicted well-groomed minus real well-groomed has an error, when you move, you're going to accumulate some error. You could say that should be white noise, but it's not going to be white noise because well-groomed is correlated with the predictor. Well-groomed hat is correlated. Well-groomed minus well-groomed hat is still correlated. So it's a subtle, the technical challenge here isn't about dealing with the well-groomed. It's about, you don't have well-groomed, you have well-groomed hat. And that's just something I want to say is like when people are talking about all this GAN stuff and they're doing conditional generation, all of that stuff, for exercises like I want to make someone look older, that's all fine. For exercises like this, when you have predictors that are not AUC of 1, these problems really show up in full force. Because you don't, people act in these models like I've got this variable represented. No, you've got a prediction of this variable represented, and that difference starts to blow up a little bit. And we can talk a little bit about it, but that's at the heart of it. It's not my inability to represent it, it's my inability to represent the true thing as opposed to the predictive thing. There are two procedures. I won't really go into it, but it's basic. It's not interesting. I'm sure one of you will come up with a better solution. So now we do a second thing once we've done this. And in fact, you get these two photos. Oh, you guys can't see it. In this one, it pops out a little bit more. What you get is what we're calling full-faced or heavy-faced. It turns out that people with heavier faces, like just bigger, fatter, wider, heavier faces, are much more likely to be released, or at least predicted to be released. So now let's see what happens. So we've now had an interpretation pipeline that had somebody look at the algorithm and say, this is what I think the algorithm is seeing. We could say, sure, that's what the algorithm is seeing. Do any of these things matter in the world for real people? So far, we've just had communication between one object and another. Now let's look and see if any of these things matter. Did you have a question?
Yeah, just a quick question. So when you were using the mechanical Turk people to try to predict, those people are trying to predict the outcome of the algorithm that you have trained?
Yeah.
It's then trying to predict the outcome of the judgment?
Yep.
Oh, okay.
Yeah, exactly. And why can't I just have them predict the real outcome? Well, because the real outcome is just ones and zeros, and there's no two faces will just vary dramatically between them. Okay, perfect. So the combination of the generative model and the predictive model is what's really allowing you to do very fine-grained matching and be able to show small differences. But to test these two, well-groomed and heavy-faced, we no longer need the algorithm. We just treat these like anything else. I'm going to take a set of images. I'm going to have people rate how well-groomed or heavy-faced defendants are, and I'm going to see if those traits predict actual choices. And in fact, this is well-groomed. The top quartile of well-groomed defendants are 28.7%, sorry, the bottom quartile are 28.7% more likely to be detained. That's 1/3 of the entire detention rate, just because somebody had slightly better hair, shoes, whatever. The heavy-faced is equally important. These are the heaviest face defendants. These are the thinnest face defendants. The gap between the bottom quartile and the top quartile is about 7 percentage points. Again, about 30% of the entire detention rate, just by having a face that's thinner. This is not related to race or skin tone. So if I simply put x-axis skin tone, y-axis average release rate, actual release rate, and I look at what happens to the well-groomed, there's just a shift up in well-groomed across every skin tone, across every race. There's a shift up when you become heavy-faced across every skin tone, across every race. So this is by way of saying those are two that we found. We've explained about 6% between, or 7% between them. And in principle, you could iterate the procedure and understand it a little bit more. I'm going to stop here and stop the paper here because I think it's fair to say everybody involved has run out of steam. And what I view it as is, why do well-groomed and heavy-faced matter? I view exercises like this as setting the table for more careful empirical work that can now explore these hypotheses per se and actually understand what these are doing. I don't view this activity as producing, I think there's a pipeline for science. We have to make decisions about what we study and carefully, et cetera, et cetera. I think we spend too little time on hypothesis generation and just kind of come up with random things. Here, you've got a material way to generate very empirically important hypotheses in a correlational sense. And now you can dive in and try to understand mechanisms. Is it causal? Is it because it's correlated with something? Now we can try to understand. And I clearly can't do that in this paper. So let me argue this is not a paper about well-groomed or some people being full-faced. I hope you see that. I hope you see it's not a paper about judges per se, but that it gives us a way to generate hypotheses about people, not just judges or from faces, but a procedure to create new hypotheses about why we as people do what we do. What are the key ingredients? Well, we need some behavior to predict. We need some data with which to predict it. But let me articulate a little bit the nature of that data. And that was a question that somebody asked me, I think you asked me over the break. A lot of times we treat data as data, But for this activity, I want to make a difference between two kinds of data, because they are very, very different. One kind I'm going to call structured data. I mean sort of tabular data. This is things where there are columns of variables. It will read things like number of previous arrests. It will read things like education level. These are data sets. They look like matrices. We often work with these data, but for the exercise that I'm describing right now, those data are unlikely to bear much fruit, and I'll tell you why. The room for surprise is limited in those data. Every one of those columns already have meaning. We collected them because we know what they mean. I'm not going to surprise you and say, it turns out, like when I said current charge matters, if I told you that, it's like, oh, kind of useful. Sure. But it was one of 40 variables in my data set. I could have just gone through. I mean, there's limits. There's a second kind of data, which I'm calling unstructured data. Take something like a mugshot. When I take a photo of a person, I'm not collecting a particular kind of data. I'm collecting everything that's in that image, including things I never even imagined. We have two ways to instrument the world. One which instruments it and pulls out what we understand, and other ways which instruments it and pulls in a lot more than we understand or conceptualize or thought of. These unstructured data, which are images, language, very rich time series. Ziad will talk tomorrow. Some of the stuff he'll talk about are X-rays. There's so much more in an X-ray than the human mind realizes. Even something like an EKG, which is just a waveform, and it's the electrical charge in the heart. It's just a waveform. There's a lot more in that waveform than we possibly can understand. These unstructured data, because they are not filtered through our knowledge of what we believe to be true, have the potential to capture a lot more signal than we ever imagined. And so the deeper point is, it's these variables that we didn't think to measure that these data contain endless numbers of possible features that we can make sense of. And then finally, we need to be able to combine that with morph, but this is where I would say the unsupervised models have gotten very, very good in the last 3-4 years. So somebody asked, why not use a VAE, like a variable? Great, there are very good VAEs. For EKGs, the VAE might work better. And so it just comes down to combining improvements in unsupervised modeling technology with our capacity to do supervised learning on these two activities that generate something. Let me stop there. That is the part that I hope to convince you that we have an ability to change the way we do behavioral science in this first part by moving forward and uncovering, I hope you can see, not just in this abstract sense, but in this pragmatic sense. We have a judicial system. Even if there was never a risk tool in that judicial system, we have people making important decisions about other human beings' lives, and if we can understand errors in those decisions, we can make a big difference in the world. Somebody said during the break, well, if this is right, why are we even allowing judges to look at defendants? Why are we even allowing judges to look at defendants? It's a good question. And so that's the kind of thing that we can now, we can ask a bunch more questions with things like this, and the policy changes could look very different. Okay, let me pause on this before moving to part 2. If there are any questions, and we can take those, and then I'll try to do part 2 fairly quickly. Yeah?
Two things. One is there much correlation between the features that you've extracted out of the image data and the other things that were important? For example, I could imagine that you would not look very clean in your mugshot if you were arrested in the middle of a violent crime.
Yeah, absolutely. Yeah. So there's that correlation you're talking about. There's another correlation. I don't remember who asked me this about the, was it you? No, I don't remember. Anyway, so somebody pointed out also in the earlier papers, like, well, what are we taking arrest to mean? Arrest is also biased, right? And so there's some subtle issue with the correlations with the other variables. So for example, suppose the police are more likely to arrest people based on their own biases, and those correlate with the face. So there's a little bit, it's hard to know how to unpack that correlation. Is that correlation simply the magnification of this bias upstream, or is that correlation something meaningful, like it's a violent crime, so you're just picking up on that? What I can tell you is that you could take a lower bound. If you say, I'm willing to take all of that correlation as genuine signal, what's left? About 75% of the signal is still left, and all of these effects still survive. So there is There is some correlation. So there are people who are well-groomed are less likely to be arrested as well. And people who are heavy-faced are also less likely to be arrested. And so there is a little bit of that. That's about a quarter, I'd say, maybe 20 to 25%. That's part of it. But and I don't know what to make of it. I wouldn't necessarily want to go all the way in, but it's a great question. Yeah.
And the other question was, I don't know, during the pandemic, I imagine a lot of judicial things had to be done over Zoom.
Yes.
And that presumably changed a lot this interaction.
Yeah.
Do you see a change in, do you have access and do you see a change in districts as to who gets released or whatever other things you're looking at?
Oh, that is I had literally not thought of that. It's an excellent question.
Because I imagine another thing that probably
Yeah, it's an excellent question.
is audio, how a person speaks, and that probably...
Now, we don't have that here, but your point could still hold, just to illustrate. If in the Zoom interaction, I don't really see the defendant's face. On the other hand, there is something a little troubling, which is when you get the packet, there is a mugshot. Like, there's just a question, why do we have the mugshot of the person on the packet? It's an absurd thing to put right there. Now, but with the Zoom interactions, I'm not sure they get the physical, so we do have the data. We could easily do the following exercise. We know when the pandemic hits. We know when Mecklenburg County switches, or we could find out. Does the predictive power of the face change at that point? Yeah. Great question. I truly had not thought of that. Yeah.
I have I'm a bit curious about the part where you have the subjects explaining why they make the decision that they guess that who is more likely to, say, get a charge, for example. Because it is sort of well known in psychology that a lot of times people make a decision or make a move first, and then our brain somehow come up with an explanation of that, but it's not necessary.
Absolutely, yeah.
So I'm wondering, could it be the case where there's actually some later factor that is actually controlling this?
Well, let me be precise as to what that would look like. If our subjects trying to decode the algorithm got pretty good at guessing what the algorithm was doing, but couldn't quite articulate what they were using to guess, then that would lead the procedure for the stuff they say to be noise, basically, because it's ex post rationalization. That is very much a real concern here, because as you say, the psychology literature calls into question our ability to articulate. So I would say first, it's an empirical matter how big that effect is. And here what we find is, in fact, there is noise. Only 40% find well-groomed. But we know that it's not noise because when we take well-groomed and predict what the algorithm will do, it does predict it. So it can't be an ex post articulation. But it is a limitation of a procedure like this, and there's just, I don't see a way around that if people are not able to name the things, but maybe there is a way around it. So we should keep that in mind. The second thing I would say is that I think in other work in talking about algorithmic versus human decision-making, I very much emphasize what you're saying, human inability to articulate what they do. And it is a big effect. For example, I didn't show you the data here, but if you go and ask public defenders, what do you think the judge is looking at? They absolutely do not say the face. I am guessing if you ask the judge, what were you looking at? They wouldn't say I was looking at the face. We know they are. So we should be suspicious of the ability to articulate. So I think there you're 100% right. And it should give us humility relative to the interpretability problems that algorithms raise when we realize humans have their own interpretability problems for their own decision processes for themselves. That's on one side. But the other side I just do want to emphasize is that when you do get people to these very narrow tasks, like this, tell me what you saw in the photo, 50%, 40% signal is not unreasonable, and you tend to get to that level. Does that make sense? Oh, I'll let you fight. I mean, you're wearing the same shirt, so I'm not sure what to do at this point.
Consider that one particular judge or nowadays algorithm judges, because maybe some particular characteristics of each of the judges also affect their
Absolutely. Yeah, you raised this question during the break. A really good question would be if we had judge identifier, could you ask, does a common judge model, a shared judge model, predict the individual judges, or do they have idiosyncratic components? What are different judges looking at? Super interesting. We don't have judge identifiers here. But in other data, you can imagine getting it. It's a kind of super interesting question to ask. Are our biases different? What do our biases look like? Great question. Yeah, did you?
I was wondering if you could share your thoughts a little bit on privacy. Because if the conclusion is that we need more unstructured data in order to do all this work, and this unstructured data is private, what do we do? And we know how to privatize structured data by now very well.
Yeah.
But we don't know how to do it for unstructured data.
I think I'm not, I'm nowhere knowledgeable enough to answer your question. So let me just give one narrow component that I think people who work on this might find useful. To me, when I think about things like privacy, I think there's a little bit of, as an economist, I can't help but think of it as cost-benefit. As cost-benefit. And if I think of it as cost-benefit, what's never very clear to me with a lot of these things is, well, what is the benefit? Like, how big is the benefit? So I view these exercises as starting to help me understand the specific and narrow benefits that might be entailed. So to take this exercise, say there are more things like this we can produce. Well, we don't need public data releases for this. What we need for this is, for example, with highly secure, even structured data, we allow researchers to become vetted, screened, seconded, and go to a private place to use that data. That's what the IRS does. That's what the Census Bureau does. This type of stuff, I would argue, is in that category, that this isn't a huge benefit like for the marketplace. It's a huge benefit for the small subset of people who are serving to interrogate the system, whether that's researchers or public advocates or whatever. And we might have different release for this kind of benefit than a broad release. Does that make sense? Yeah.
Thanks.
Yeah.
So we were given this decision right now at finite, right? Given by a judge. But correct me if I'm wrong, but my limited understanding of the American legal system is that the decision is given by a jury. And the jury has like people of very demographic factors and we need to look at.
Sorry, yeah, no, this decision is definitely by a judge, and I'll tell you what I mean. It's worth, when you get into these topics, I think, and you're not working this, but for the rest of you, it's worth, if you get into any of these topics, the minutia of context really matters. So now I'm going to get on a pet peeve. Here's my pet peeve. If you just look at papers talking about risk tools in criminal justice, they actually pull together two fundamentally different problems. Problem one, sentencing decisions by judges and juries. Problem two, pretrial release decisions. Now I see why they're making this thing. In both cases, a person goes to jail or not. Actually, that's technically not true. In one case, a person goes to jail or not. In the other case, a person goes to prison or not. These two decisions have very little to do with each other from the point of view of criminal justice. Pretrial happens very shortly after arrested, 24 hours. It's made by a single judge who might talk to you for 2 minutes if you're lucky, and who is not making any decision about your case. They're making only a prediction about your flight risk and your crime risk. And that's all they're allowed to do. Sentencing is made by a jury, if it's a jury trial, or maybe just a judge, but this complex system over a trial that takes place over months, and where the goal of the judge is not flight risk. Why would a risk tool be? I mean, yeah, it's sort of useful. A risk tool may be useful to the judge because they may care about recidivism, but they care about things like justice. What is the right punishment that fits this crime? It's just a different objective function. So when you look at it as payoffs and what's going into the decision maker, they're just totally different activities. Does that make sense? And so as you work in these areas, like whether it's criminal justice, hiring, or health, I hope what I've given you a sense of is it's really important you go all the way down to the very specific decision and ask what are the payoff functions, what do the decisions look like for that decision, Because at some higher level of abstraction, those details get lost, but those details matter a world for any of these things, because we're trying to interrogate a human decision maker. They're not working at that level of abstraction, they're working at this level of abstraction. Does that make sense? Is that? Yeah.
So, the thing you mentioned on the previous slide about getting summarizing patterns from unstructured data. So, I want to relate this to something you mentioned before about interpretability. So, would it be like my worry is that if we were able to get some surprising things from unstructured data, we might reject those things on the premise that they're not interpretable. And
Oh, I see.
and basically, whatever is interpretable to us is only expressible in terms of data that is structured and that we.
So good. So let's talk through faces to make that concrete. There are domains that have the following feature. We can think of 10 things, and we've measured those 10 things. And I can't think of any more. This procedure is not going to help you with that, because you're only going to, if you can't think of the 11th thing, this is not going to uncover the 11th thing. There are other domains where I can think of 1,000 things. I've measured 10, but I can think of 1,000. This will very much help you with that. So when it comes to human behavior, there are many things of that variety where we, in a face, if you just said, go ahead and measure the features of the face you think are important, and you're like, I guess I would pick these 8. There's another 992. I don't know if I picked the right 8, but I picked whatever. It's in the set of things where you've got a rich descriptive vocabulary of a lot of different possibilities, but you've measured them implicitly in your unstructured data, implicitly, but they're there, but explicitly you have many hypotheses and you wouldn't know. Does that make sense? And that's the use case here. It's specific, doesn't apply to lots of things, it doesn't apply to everything, but I think it applies to several things. So. Great. Were there other questions? Yeah.
I have a process question. It works like you have the data and then we're kind of continuing on research to this day. In parallel, it feels like we just kind of use the same data sets and push them. So you have recommendations.
Yeah, let me answer both. Those are great questions. So for the first one, it's related to the answer to the second one. If I was being very honest, here's what I would say. In this talk, I gave it a sort of a surprise look, it's in the face. But, our first paper that I showed you earlier also had data. We could have run this procedure there, but it was just structured data. So we spent a long time finding a place where we could get the data that we had in the first paper along with some unstructured data like the mugshot. So it's not a coincidence. I mean, it didn't have to be that the mugshot was important, but we happened to chase it to get that data, which is related to the answer to the second question, which is, I think there's a divide between how much energy you put into the acquisition of new novel data, whether that is collection or more likely finding it, finding a partner, finding a location, versus how much you take an existing data set and just exploit it. And I'll just point out one thing I'll point out without judgment, and then one thing I'll say as advice, which you can therefore ignore. So the thing I'll say without judgment is that there's a massive cultural divide between social scientists, like economists, sociologists, and computational scientists on this front. Computational scientists, on average, tend to invest less time in the acquisition of new data than social scientists, and in fact, a lot less time. So if I said to a PhD student of mine, I have an idea, in fact, I did just say this to a PhD student of mine, why don't we go and just talk to a bunch of firms in this area until we see if one of them would bite and blah, 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 blah. Basically, I was suggesting to him a 6-month uncertain activity with real effort, that the effort that he put into that probably was enough to get one conference paper. Because it's work to track these people down, to talk to them, blah, blah. Now, if I said that to a CS student, I think it would be a hard hill for me to convince them to climb. On average, some people would do it, but it would be a harder hill. With an economics student or a social science student, they're much more likely to say, sure, I'll do that. So that's the first descriptive observation. Now my advice part. I think you could rationalize this descriptive difference by saying the career incentives match it. You know, these papers are short, these papers are long. If I spend all this time getting this data set and I only produce one paper, what impact will that have? Blah, blah, blah. So I think it's entirely reasonable and it's rationalizable that there's this difference. So with the caveat that it's easy for me from my position to give all sorts of advice. I'm just gonna tell you what I tell my students, which is, I think the winds are changing. I think because so many people are playing the numbers game, there is an outrageous number of papers that are being published. An outrageous number. And as a result, the sheer volume of papers is dramatically increasing the return to quality or novelty or something interesting. That would strike me if I were a student and purely focused on professional success to say, maybe it is worth my interest in going out and really getting a data blah, blah, blah. That's piece one of my advice. But piece two is more personal, and again, you should just ignore it. I didn't come into this job personally as a job. Like, I'm in this job because I love research and ideas. That's the only reason I'm in this job. I barely think of it as a job. And as a result, for a lot of my decisions, I kind of think it's important that I ask myself, where do I feel I can have the biggest, kind of, with what limited skills I have, the biggest influence I can have. And if you look at it that way, for all of us, I think the answer is to decorrelate. As a profession, we're all better if we decorrelate because we all go find new things. So I would say whether it's professional success or some, at least my own personal ethical norms, I think it's good. You should go out, like invest and try to find new things. You'll be happier because you'll have something novel and exciting. And you'll be like, wow, this nobody's worked on, like Alexandra Choldachova is a great example of this. Nobody's worked on child welfare. So she went and she got this very interesting thing. It's very enriching, and her students who worked on that. So I think that I would encourage you to, I believe, but don't come back to me and tell me, boy, were you wrong, but I believe the professional incentives align with the personal joy that you will get, and that you really should try going in that direction. And I think what I will say is that direction is a lot easier than you think. It's time intensive, but there are lots of organizations out there with data who would love people like you to work with it. It's a matching problem. It's finding them. That's it. But you just make enough calls, you'll get there. And if any of you get interested, you should definitely email me and I will give you advice or direct you to people or whatever, but a lot of people are interested. That was not the long answer you wanted. Did I at least answer your question? Or you want to push back on me? Or does anyone want to push back on me? It's supposed to be a summer school. You're the future of our profession, so you should push back. Somebody looked like they were going to push back. No one wants to push back? You guys are all so much nicer than my PhD students. Any other questions? Oh, did you? Oh, no. Okay, so we've got 20 minutes. So let me, because then we have a little bit of time to talk afterwards, why don't I tell you a thumbnail sketch of the other direction. So the other direction is, what if we were all to learn a little bit more behavioral science? How would that change the algorithms that we designed? Okay? And this is based on two papers, and I'll try to put them together. So the first paper can be pithily summarized by something that happens to me a lot, so I've stylized it into a little story. Okay? I go over to a friend's house. She wants to hang out. I say, great, we'll hang out. And because she's being friendly, she has put out a bowl of Doritos. Now, what happens shortly after is that I have eaten all of the Doritos. Now, my friend is a good host, so she sees Sendhil likes Doritos. So she puts out more Doritos. And I promptly eat it all. Now, this could continue for some time. So just like the iteration of morphing, I'll stop. You can see where the story ends. It kind of ends here, with me saying afterwards, I'm definitely not going back to that friend's house. Because I'm so sick. I ate a lot of Doritos. I don't want to eat all those Doritos. So what went wrong? What went wrong with my friend, with this little event? After all, she was being extremely polite and looking out for my desires. Well, the first thing that went wrong is me. Let's just assert I got a problem with Doritos. But there's a second thing that went wrong, and I'm not trying to blame somebody else for my problems, but I want to argue the host made a mistake. I think the host did something subtly erroneous. But what exactly was the mistake? Well, she made a misinference. She said, Sendhil loves Doritos. That's not entirely true. I mean, I do like them, but not as much as I eat them. So she makes a mistaken assumption. If he's consumed them, he wants more. So the first thing I hope you take away of where behavioral science can help us is to understand that that mistaken assumption is not about me or Doritos. And I know it sounds like I'm just making excuses, but it's not me. It's pretty universal. You all have your own version of Doritos. For example, there's some wonderful studies in the food domain where if people are buying in person, they're more likely to buy ice cream. In the moment, you really want stuff, you're like, oh, I get ice cream. But if I'm buying for some distant remove, I'm less likely to buy ice cream. I'm likely to buy vegetables and other things. In movies, if I'm just making my choices for right now, I'm more likely to stream action movies. But if I'm making my choices for the future, like mail order, I'm more likely to pick documentaries. That's because in the moment, I'm going to stuff my face with Doritos. But if I think of what I want tomorrow, it's not to stuff my face with Doritos. And that tension is pretty universal. There's a large behavioral science on that tension. And that's what I want to argue is the broader lesson. So what's the broader lesson for algorithmic design here? Oh, please.
I just want to make a point, because I'm guessing where you're going with this. I'm going to say your host didn't actually have your interests at heart.
It's totally possible, yes.
And this is where the problem is going to come from.
I agree. And what I want to...
Not scaling the Dorito supply responsibly.
So I think there are two problems. So I think one problem is my host doesn't care about me, which is a pretty cruel thing to say about her, Cynthia. But anyway, no. But the second problem, which I want to argue is the one that is buried in there, is the misspecification. And so I want to separate out the difference in incentives with the difference in misspecification. So let's come back to it for a minute, and then I think we can... I completely agree with you, there's an incentive problem. I'm not trying to minimize the incentive problem. Okay, so where does all this play? If I go onto Amazon and I search for gifts, okay, just think of this example. I get this, then I get this. Actually, weirdly, I get two colors of this, and then I get this. And why do I get these? It's because if I was studying choice, I would say, oh, how did Sendhil choose between these? Well, I chose that. That's actually quite a good gift. And we'd be understanding human choices. But in the modern world, there's actually an ocean of choices. And there's something that curated my choice for me. Let's call that algorithmic curation. It's a converter of this infinite ocean, or this very large ocean, into a ranking, into something. Now, human choices is a study of behavioral science, but the curative activity is more algorithmic science. But what the Doritos example, I think, and I will come back to the incentive, that's an issue, but the Doritos example tells us when we write these curation algorithms, we make a behavioral assumption. And Put aside what happens in the world for a second. I want to now just go back and attack textbooks. The textbooks, the things we teach undergrads, the foundational things that we teach people by how to go about curating choices, whether they're recommender systems, ranking platforms, all of them, they make a faulty behavioral assumption. So what is the faulty behavioral assumption? Well, all algorithmic curation looks something like this stupid pipeline. Hey, we've got data on user preferences. We're going to train that procedure and build a curator so the algorithm learns what people like. Like if you're teaching an undergrad class, you put up a slide like this. But this slide has an error that every behavioral scientist would tell you is absurd. You don't have data on user preferences. You have data on user choices. And you learn what users choose, not what they like. And you are engaging in the fallacy of reveal preference. Built into every curation algorithm is a deep psychological mistake, a misspecification of preference. We can model the psychology and precisely study the consequences of that misspecification. What I think that does is it allows, and that's what this paper does, the challenge of understanding what users want. And maybe I will just point you to that paper. And I think what this paper does is, I think Cynthia's point is very well taken. I don't want to argue this is the reason why social media or other things are producing terrible outcomes. But I want to point out this is a contributor of the reason why we see these things at scale. And if we understood the misspecification better, we would then be able to understand things. So what do we get out of it? I'll skip the model itself. What do we get out of this misspecification? I'll just tell you quickly what we get. Is that engagement maximization can fail to maximize utility, but under some conditions, it actually does very well. Because reveal preference doesn't tell you we always fail. It says for some things, salad, nuts, and other things, engagement equals whatever. For some things, it's way off. And what the model tells you is that the key learning problem is not to predict choice from behavior. It's in the manifold of all possible content to predict which kinds of content does the engagement gradient go in the same direction as the preference gradient. In other words, when does, for what kind of content, and when can you do that? Well, it turns out with a little bit of auxiliary information, you could actually start making progress on this problem. For example, if you collect not just choice data, but you also collected a little bit of user survey data. Not a lot, but just a little bit. You can combine large amounts of choice data with small amounts of user survey data to learn this manifold. There's just one example. I'm not going to go through in detail, but at least does it kind of make sense to people? I don't know if you have questions about this, but this is giving you a flavor in the time I have about how importing some of these ideas could give you something. Okay, let me make it more concrete and tell you an empirical case where we see this. One thing we could import is self-control. Another thing we could import is this terrific behavioral insight, which I think is wonderfully summarized by a New Yorker cartoon. I don't know if you guys can see this, but this is 2 levels deep. This is one of my favorite New Yorker cartoons. Does this make sense to anybody? When you go home, it'll make sense to you. No? Makes sense to anybody? So, what is that? Is that a duck? Okay, now you see it makes sense. So the psychological insight this really has is that there's a bias known as in-group bias, which is very strong. Let me tell you what in-group bias is. In choices, we favor our own group. But importantly, we favor them more than our preferences want us to. Does that make sense to everybody? When you decide where to go and sit at the conference dinner, without intending to, you might end up sitting more likely near a group of people like you than you would have liked. That's not what you're intended to do, but it's automatic. But the bias has structure. In that sense, it relates to the self-control problem. It's larger when you behave automatically. In other words, when you make low deliberation, quick decisions, each with very small consequences, you're more likely to engage in this bias. What I mean is to do more of it than you intend. I don't know if you all know of any low deliberation, quick choice, low consequence decisions that are out there, but I know a few. And what that means is that when we train algorithms on these social choices to curate, we're trained mostly, but not always, on these automatic choices. Which means the algorithms are going to learn our in-group bias, not our in-group preference. Which then, so just to make it concrete, I have made a friend with somebody who's not like me, okay? They're in my friend thing. When their post shows up, think of how precisely Facebook is measuring my choices. How long do I linger when I'm scrolling past? I mean, that is very automatic behavior. That's all getting pulled in to the post ranking. And I probably linger less on outgroup members. It's not what I want. I mean, I made friends with this person. It's not my preference. But the algorithm says, oh, Sendhil likes this person less, and then proceeds to rank them. So behavioral science insight 1, choices are not preferences. The wedge between the two depends on the context of the training data. Does that make sense to everybody? Okay. So let's see how much this matters. I'm going to do a lab experiment, and then I'm going to do a field experiment, okay? And I'll do this very quickly, but I can give you feedback. Here's a lab experiment. We have people look at movies like this, and they are choosing which movie they'd like to actually get for free to watch. Now, these movies are recommended by people. Look, Kyle recommends, Heather's, blah, blah, and they're moving through and see that's like Kyle is there, Dylan is there. It's just a feature of who's recommending. And we randomize the names on these to be either stereotypically white or stereotypically black. And subjects get these incentivized choices, so one of the movies they'd actually get free. And the random assignment of names means there's no relation to the underlying movie. So the question is, does click rate depend on in-group identity? But recall, we have a key prediction. It's not in-group bias is always there. In-group bias is more likely to be there when I'm choosing quickly, choosing automatically. So what we're actually doing in the lab experiment is that we manipulate how long people have to choose. Are they spending a long time on this activity, or are they spending a quick time on this activity? And then what we have is we have training data from two worlds. Randomly assigned subjects who are choosing movies fairly quickly. The same subjects, or another randomly assigned group, who are choosing movies a little bit more deliberately. I'm going to take that training data, and I'm going to train a recommender system to recommend movies to both populations. Now, their preferences are the same by construction. What happens to the algorithmic recommendations when we train in these different worlds? And so what you find is you in fact find when it's trained in the deliberate behavior world, there's a small but insignificant difference between in-group and out-group posts. But trained in the more quick decision world, the algorithm is going to be recommending movies by the in-group at a much higher rate than by the out-group. So this is just helping you see in a lab experiment how the bias plays itself out, but it's not a fixed bias. It's determined by the context. Okay, so it's worse than mirroring. I just want everyone to see this. This is a double penalty, because here's what happens. Out-group posts are ranked lower, so I never actually get there. But on top of it, since I'm also deciding when I do see them, I'm less likely to click on them. So now I've taken my single bias and I've doubly penalized it. It's already going to be there through my own choices. Now the algorithm has pushed those to the bottom. So there's now a double penalty. Okay. So does any of this matter in the kind of industrial scale algorithms we see? So here's what we did next. We did an audit of Facebook where we got a bunch of subjects, I'll skip what these are, and we audited how newsfeed ranks and how people you may know ranks. Both of them are curation algorithms. But people decide differently in how they interact with newsfeed than they do with people you may know. We did a bunch of surveys, and what you find is, in essence, if you ask how many seconds do you think about it before you click, hover, linger, accept a friend request, etc., as you might imagine, interacting with posts is automatic, accepting a friend request is something you spend quite a bit more time thinking about. So same company, you see big differences in the context of choice between newsfeed and people you may know. Now we have an audit that we're going to do for both algorithms. So here's how we're going to do. These are an external audits. We recruit audits, we recruit subjects. They're going to screen share while they're scrolling through. We're going to ask subjects afterwards, how much do you like the post? I don't care about your behavior. I just want to know how much you actually like it. So now I'm trying to elicit your actual preference. Then I'm going to measure the algorithmic ranking. So the good news is, if I put self-reported preference for the post, y-axis, the rank, you find that in fact, posts that are liked more are ranked higher. But at every level of likingness, outgroup posts are ranked much lower conditional on preference. So much so that about a significant fraction of your friends who you have chosen to be friends, for the posts you like about them, they're being hidden from you further down the timeline by the algorithm. Now you could say this is something about Facebook. Well, let's go and see what happens on people you may know. Do the exact same thing. How does it rank order friends? And there you find, however you measure the ranking, no difference at all. So there's no in-group bias in the people you may know algorithm. It's only in the newsfeed algorithm. Which is, I think, consistent with what you saw in the experimental evidence, which is you had one context with more automatic behavior, and the audit study shows an algorithm at scale with lots of in-group bias. Another where the behavior is more deliberate, and we see no in-group bias of the algorithm. How general is this? Oh, yeah.
Yeah, it's occurring to me that my interaction with the newsfeed is private to myself. No one knows, but my interaction with who I accept as a friend is public to that person.
That's
so
right.
There's also something about how I perceive.
It's absolutely right that if I just showed you this fact, we could probably generate quite a few things. And I'm not saying none of them are right. To me, I think I view it more from this direction, which is in the lab when we can do careful control, we see this effect as big. In the field where we can't do careful control, but we at least see if the pattern appears in an industrial scale algorithm, we see it there. I definitely cannot tell you I know the cause of this, but I can tell you it matches what you're finding in more controlled conditions. Does that make sense? Okay, how general is this? So the next thing we said was, well, that worked with in-groups and out-groups as defined in the US, but what about in a totally different place? What if we ran it in a totally different context? So then we went into India, where in-group and out-group is now defined by religion, and India is not like the US at all. And again, you see the exact same pattern, which is the newsfeed algorithm for Hindus demotes Muslim posts of their friends they've already made, and for Muslims, demotes Hindu for posts. But in helping you make Hindu or Muslim friends, it shows no gap at all. It's just showing you that. So what you see here is that same pattern, totally different country, and partly the reason I'm doing this is because some of the biases you may imagine that are kind of like display and look to others could flip in other ways here as well. So for example, it's not obvious for some categories of Hindus that they want to look like they're making some. So by way of saying in controlled lab conditions, you see that the algorithm creates this in-group bias, and it's a meaningful problem on Facebook across 2 different countries. And it kind of opens up important questions of how we design algorithms. So for example, even within newsfeed, they've got many measures of behavior, some of which are more and less automatic. But we're pooling them together because our underlying model is users like or don't like. Our underlying model isn't, there's a latent level of likingness. Behavior partly represents it, partly has a bias, and the extent of it depends on the behavioral measure. Then we might take lingering and hovering as very different than liking and commenting. We may put them at different levels. And it has obvious social impact. So I hope from this second piece, what you'll take is that by importing some of these insights, we might change some of the misspecifications we have in these algorithms that we're building and deploying. But together as a pattern, I think there's a way for a more fruitful interaction between what we know about people and what we know about and how we go about building algorithms. So let me just list the relevant papers here, and I'll need to end here now. So thank you for all of you, and it's been such a delight.